So 2.9. The term of a single deposit. What do they mean by the term, the deposit? Yeah, the number of months or number of years, right? And so you could probably guess in any of our given little formulas there, we'll be solving for what part of it? The t, right? And where do we find the t in these formulas always? Up in the what? And the exponents. We can't just do like dividing and stuff. What does that look? Come on.
I hate square root.
No, it's not going to be square root. Square root would only work if we were squaring something and had to undo it. So, do you guys remember what undoes an exponential function? You had algebra 2, so you should know. Nope, that's square root of a negative. Logs, the logarithms. Logarithms undo exponents, and exponents undo logarithms, by the way. It's just like multiplication undoes division, and subtraction undoes addition, right? Logs undo exponents. We'll get to that in a bit. So the terms for the maturity of an investment, right, is the time horizon. I think I've used the word horizon of maturity, right? So an investment that matures or has a horizon of like a year or less, consider that short term, and the longer than that, consider the long term horizon or long term maturity. Okay, like a bank CD from 1 year would be short term, 6 months would be short term, right? You know what? Okay. All right. So before we get to the logarithms, take a look there at example 1, page 121. So after inputting values for VPNR, and just using the plain old compound interest formula, right? They want us to determine the interest rate for this account expressed as 8%. What do you think about that? Okay. So, in example 1, we won't really, let's see here. So we have, like, they give us 1061.52, right, is the result of our, let's see, 1,000 times 1.01 to the 2t, okay? That is this here, our formula, B equals P times 1 plus R over N to the NT, right? You see how I wrote it underneath so it kind of lines up? And they want to know what the annual rate is, that 1.01 up there. Do you think it's 0.01? Huh? Well, that's only, it would be if it was only compounded annually, right? And so, because if N was 1. But is N 1? Is N 1? It's 2, right? So that complicates what the rate is just a little bit, right? Well, let's think about this here. If we know that N equals 2, right? We know that R over N here, what does R over N equal? What does R over N equal in that example? Geez, I just drew arrows to it, or an arrow. Huh? 0.01. So we know what N is, don't we? We know it's 2. Couldn't we solve this pretty easily for the rate? R over N then, R over our N is 2, is 0.01. So it's a little less complicated than you thought, right? So what does R actually equal? 0.02. So the rate, 0.02, which of course is 2%. All right? Yeah, if it was compounded annually, you could just say, yeah, the rate is 1%. So you get that, like, if it was compounded monthly, it'd be R over 12 equals that, right? You multiply by 12. Okay? Get the idea there? Not too tricky, is it? All right. When you guys try that with the check, see if you can work that out, because you'll have some homework problems like that. In the check, I think they gave you 2148.85. Equaling 2,000 times 1.006. Two of them. To the 4t. Okay. See if you guys can solve this for R. What is the actual annual rate if you were given that setup? Is it 0.006? No, it's not. Clearly not compounded annually. You know, our n equals 4. So what's our setup here? To solve this for the actual rate. We'll go get that up here. What is it? Oh, yeah, right. Well, not really. Because probably 0.006 is not our rate. That's our quarterly rate. R is the annual rate. So we don't know that yet. But we do know that R over N equals what? And we know what N is. Right. So R over 4 equals 0.006. So what does R equal? Yeah, 0.024, which is 2.4%. Right, you get the idea? Those are kind of simple. You might not leave that and show today. You might stare at it for a while and just try to say, yeah, it's, 0.6%. Okay? All right, we'll skip the extend there. All right, well, let's talk about logarithms because we're going to need those to get after our variable t up in the exponent of these formulas. So a little review of logarithms from your Algebra 2 course. Hopefully they were able to get somewhat into that in our shortened time. So logs, they undo exponential functions. Of the same base. We're dancing around. Okay. Undo all exponential functions of the same base. Okay. In other words, they're inverses. They undo each other. Okay. So, and you might have seen this. Just what is it log? If log base, and the base is a little subscript down there, B of C equals A. Do you guys remember that that's equivalent to saying B to the A power equals C? Right? Then B to the A equals C. That's what that log is saying, wherever the base is B. Okay? Like you could have log base 3 of something equals something, right? And something in the third power equals that other thing. Okay? And do you, well, let's see, here's another thing, by the way. Here's another thing about logs and exponents. First, let me do this. If I have just the log of x with no base written, do you guys remember what you assumed the base to be? No, not 1. 10, right? Base 10 is the same as a log base 10, but if you don't see the 10 written there, it's assumed at 10. Or you might have this. Remember ln? What's that? Natural log, remember that? From algebra 2, the natural log. That's the log base what? If you see ln, it's the log, remember the e, right? This is your natural log. Okay? Euler's number E, natural exponential, which is developed in the pursuit of finance. How do you handle exponents when you have logs? Remember, you have that log of something with an exponent, doesn't the exponent come out front? Remember that? Well, we're starting to see a little method to get at the exponents maybe now, right? Okay? So if I have something like this, log base b of c to the n, right? I can rewrite that exponent as multiplication and just bring the n out front, equals n times log base b of c. And look where that exponent that we're going to want to solve for is out there. Okay? Or if I take a log of the same base of something, let's say I have log base 5 of 5 to the x, right? So the exponential function is 5 to the x. I'm taking a log of the same base. Didn't we just say they undo each other? Right? This log, if it has the same base as this, they undo each other, and I'm just left with x, the thing in the exponent. So another way to get exponents of logs, which is what we're going to need to try and do here. Okay? Does that make a little sense, maybe? Probably it'll start coming back to you once we start doing some of these things here. All right? So let's kind of keep this in mind. A little quick logarithm review, which we need to use to get on our exponents, because if you're learning here in finance, there's a lot of exponents to deal with. Okay. Let's take a look at example 2. And in the middle of page 122, they go through some examples of how to work with law, and there's a couple of typos in there. So let's just, I think I covered it with this. You're going to learn more from just doing some of these. Let's go to example 2. I want us to rewrite n as exponential. I guess that's from example 1. Compound is as a logarithmic equation. And write an expression for the term t. In other words, solve for t. Okay? So she had, go to example 2. And there's 2 ways to solve logarithms, right? So for each of these, I'm going to show you both, and you guys can pick either way you do it, okay? Either way you want to do it. So she had, well, so I think I'm going to reverse this. I like to write it the other way because I like my variable on the left. Hope that doesn't bother you. 1,000 times 1.01 to the 2t equaling 106.152. Okay? And they kind of like us to solve this for t in terms of logarithms. Well, we have this exponent up here, right? So you're probably thinking, okay, I'll take the log of both sides. Well, not yet. The very first thing you have to do, it's not done, is clean this up. I just want a pure exponential function, okay? This is that pure exponential function. Before I take the log, I want that by itself. So what do you think I should do first to both sides of this equation? Divide both sides by 1,000. So then I have my 1.01 to the 2t, right, equaling, oh, what does that come to there? mess there. 1 point, oh, get duh, 3 zeros, 1.06152. 1.06152. Okay? And now I can either take, so what's the base of this exponential function? What's the base? 1.01. So if I took the log of base 1.01, I'd get the 2t out of it, wouldn't I? So here's one way to do it. So let's take the log with this base. Log base 1.01 of 1.01 to the 2t. But what I do to one side, I've got to do to the other, don't I? Right? Log of 1.01 base at of this 0.6152. Okay? So what happens over here? Yeah, these undo each other, so I have 2t equals this, base 1.01 of 1.06152, and then I just do what? Divide both sides by 2, don't I? So t is going to equal log base 1.01, 0.6152, all over 2. And there's some you can put in your calculator, because your calculator allows you to do logs in any base. Doesn't these kind do? A lot of calculators don't. And so you think, okay, how do I do a log in a different base to undo these things? Right? There's another way to do this. Let's try it a different way. And by the way, go and put that in your calculator. What do you get? I don't have it. You get 3 years, don't you? Okay? So it'll take 3 years to actually reach that goal there, for that to happen. Let's try it a different way. Let's take just a regular log base 10 of both sides, okay? So let's go back. So this is right. And you guys can pick whichever way you like. I think kids kind of like the second way a little better sometimes, right? So let's say we've already cleaned it up, right? We've got 1.01 to the 2t equals 1.0652. It's just instead of log of base 1.01, let's take log base 10, because like most calculators you run into in your life are just going to be base 10 log or base e. Right? So let's take the log base 10, I don't have to write it, equals the same on this side. Okay? But that exponent rule, right, that 2t up there, remember I can move that out to the front, can I? Remember that rule? So another way to get our exponent out from here, so I could rewrite this like that. 2t times the log base 10 of 1.01 equals log base 10 of 1.6152. And now what do I do to both sides? Yeah, I might as well divide by 2 as well, shouldn't I? Get the t, I could do, instead of doing 2 steps, let's save ourselves a little time, right? So let's divide this side by 2 times log base 10 of 1.01 divided by 2 times log of 1.01. So then we have t equals, now be careful, right? When you put this in the calculator, you better group the bottom and see if you guys get 3 years doing it this way. You group that denominator, parentheses. Especially if you're not like a run-of-the-mill calculator or something like that, on your phone or whatever. Were you able to get 3 years with this method? Okay. So you guys get the idea. When you solve with logarithms, I could either take the log of the same base and like undo it, cancel it, like addition and subtraction, right? to undo the exponential. Or I could just take the log base 10, bring the exponent out in front, and just start dividing both sides, right? Does that make a little sense? A little more reason. Okay. All right? So we're able to solve for time now because we have logarithms. Let's skip the check on this one. This seems like an unnecessary thing. And over on page 122, 123, they go over this change of base formula. Like some calculators only have base 10 or base E, so you need to change a base formula to switch everything to that. When you solve it this way, that's the change of base formula. That's it. It kind of happens naturally when we do it this way. So I'm not even going to teach you to change a base formula, okay? All right. Do that second way. Don't worry about it. Let's go then to example 3. That's change of base. Yeah, we're going to skip example 3. All right, so let's go to example 4. Example 4. Nancy and Bob. Something there. We don't know. We want to know. They want to renovate the kitchen sometime in the future. Sounds like we're going to have to solve for T. Well, the deposit is $16,000 in the account. Compounded monthly 2.4%. How long will it take to reach $20,000? All right, so we're going to use our, and I like to write these in reverse, as you know, right? Compound interest formula, right? So we're going to use the 16,000 times 1 plus, what was it? 0.024 over 12 to the 12t needs to equal 20,000. All right. I hope you guys don't mind me writing this in reverse. Hopefully my variable goes where I want it. Okay? All right. So if I want to solve this thing for t, the time, what do I need to do first before I start taking logs? Simplifying there, sure. Yeah, okay. Well, we could do, I think we could do 2 steps in 1, right? But yeah, let's just go ahead and do it. Yeah, let's do it. So in the parentheses, we have what? 1.002. So 16,000. Times 1.002 to the 12t equals 20,000. Could have done this in 1 step. But now, before I take the log, what should I do? I clean it up. Get pure exponential function, right? So it would leave me, so if I divide by 16,000, so 1.002 to the 12t ends up equaling 1 point something. 1.2, 1.25. No, it's not. Yeah, it is 1.25. All right, so there's 2 ways we can do it. We can take the log base 1.002 on both sides, or log base 10. Which one do you guys want to do? All right, let's take the log base 10 on both sides. Either way. Log base 10 on 1.002 to the 12t. Same to the other side. So that exponent does what now? Comes out front, right? I'll move up here. Room.
Rachel Housing, can I go off, please?
Oh.
Rachel Housing, can I go off?
12t times log dog 1.002 equals log base 10 of 1.25. When I divided both sides by 16,000, remember? When I cleaned it up. Okay? Now I just divide both sides by what? Yeah, might as well do the 12 and the log right at the same time. So divide this by 12 log 0.002, same here. So we end up with T. Hopefully you get about 9.3 years. Okay, so that was our second one. Glad you guys picked that one. It seems like kids always pick that one, so we use a different base. But your calculator will do that other base. All right. I want to do the check though, but now I'd like you to do it the other way. Okay. So the check for example 4, I'd like you to use the other method. I want you to use the log of the same base. Okay. So set up your equation. $500, 1.2%, right? Compounded quarterly, so it's over 4. So the 4T needs to equal $1,000. Okay? So you guys take a minute, and I want you to solve that for the amount of time in year. T is time in years. I've gotten it down to where you can start taking the log of both sides with the same base. What's the base of the log you're going to use, guys? 1.003, because that's the base of that exponential. So if we do it this way, log base 1.003 of 1.003 to the 4t is log 1.003 of 2. Right? So these two undo each other, and we're left with 4t equals this. And then if we, I'll just go up here to save a little room, divide by 4, we get t equals log. My 2's way up there. Of 2. This on the calculator should look like this. Let's go to that thing there. What was it? Just lost my place. Where's log? Control log. And that goes right. So 1.003 of 2. This whole thing divided by. What are we dividing by? 4, right?
Yeah.
Oops, got one up there. No. One more down. I know. Divided by, it keeps doing that. Oh, because that's not right. Okay. It looked funny, didn't it? 7.8 years. Okay. And if you did it the other way, you should get the same answer. Where's my... Huh. Oh, there it is. 57.8 years. All right. Okay. Well, what if we were using continuous compounding? Right? We have a different formula. It's not the compound interest formula, right? The continuous, PEDRT. How do we solve in that one? What's the base of that, the PEDRT? E. So, sounds like natural log might be the natural thing to use here, right? So, example 5, we guessing something's compounded continuously. Peak size deposited 8,000, continuous compounding 3.7. How long? T will take to make $10,000. Okay? So we're doing the B equals PE to the RT. So the principal is 8,000. E to the 0.037 T needs to become $10,000. Okay? Well, I can undo that natural logarithmic base with a natural logarithm. But I have to do what first? Clean it up, right? Divide both sides by 8,000. So we end up with E to the 0.037 T equals, what's 10,000 divided by 8,000? It's 1.25, isn't it? Right? Well, let me undo that exponential function, right, with the natural log. Natural function, natural log, right? So if I take the natural log of E to the 0.037 T, got to do it to both sides. And most calculators will have the natural log on it as well. The base 9 and natural log. These ones have everything. Okay. Remember, natural log, right? Natural log of x is the same thing as log base E of x, right? Just parenthetically there. And so won't these two undo each other? And what's left when we do that? If this cancels out that, what's left? Just this, the exponent, right? One more thing left to do. What's that? Divide by what? Well, you guys aren't very participatory today. Sorry. It's enormous. Yeah, it's not smooth. It's not a smooth brain. And you should get 18.7 years. Would this work with the other method? We just took the log-based kind of both sides. Would that also work? Yeah, right? We'd get to the same place if we took the log-based kind of both sides, wouldn't you think? Yeah, oh, man. No, I'm sorry. I was looking down at the check, guys. My mistake. It's not 18.7. That's the answer to the check I just gave up. How about 6.03 years? Silly me. All right, well, let's just try the check and see if you can get 18.7. How about that? Look at the check. How long would it take example 5 to double? In other words, go from 8,000 to what? 16,000, right. Okay, so work through, solve that thing. Let's do it the other way. Solve it by taking log-based time on both sides. We already know we can use natural log, right? take the log base 10 of E to the 0.07 T. Use your exponent rule.
Wait, yours works too?
Yeah. There's our 18.7 years. Okay? So now we have a tool to solve for time, right? So when you were learning logarithms back in kindergarten, you probably wondered, you know, as a kindergartner, when am I ever going to use these logarithms in real life?
I don't think that, you know, people play that.
The playground, well, yeah, why not? You have to the playground doing logarithms, exponential functions with all your cool friends.
I don't even know how to
Probably not. Probably not. But some kids learn at Tots Learning Center there too. They, I don't want to. With the TBM,
Has anyone ever told you kind of stuff as the frogs?
Kermit the Frog.
Yeah,
Huh.
I've been thinking about that for the past.
Sometimes when I get excited.
Yeah,
Yeah. Sure it's Kermit?
yeah, it's Kermit.
It's not Burger Ernie?
No, it's Kermit.
Or Elmo? It's not Elmo. Maybe it's Oscar the Grouse. Or Animal.
It does,
Animal?
yeah,
Dumps.
yeah.
Yeah, I like them. No, you know what I like? It's not Sesame Street, it's the Muppet Show. You see the Muppet Show, it's a variety show with
Yeah.
Muppets and there's a big giant eagle. Stupid thing.
Oh my God.
That thing cracks me up. And of course, the Swedish chef is awesome. But anyway, let's go back to this one be a good one.
Why don't we just do the last
So,
one?
so okay, let's do example 4. All right, so let's go back to example 4 and try and do that one on the TBM and make sure. So we have to think about it. It's not as straightforward as you think, right? So our initial deposit is 16,000, the rate is 2.4, N is 12, right? And we want to solve for T. And we should get this 9.3 years. But let's look at it and see what happens. So the menu, finance, both you guys, I want you both trying this here, right? So in example 4, let's try, now the N is compounded monthly, right? So we're going to leave that blank right now. Well, that's the only thing that's going to have time in, isn't it? Because don't we put our N times T in here? The T is in here. Let's leave that as 0. Yeah. Okay. You with me now? Now the rate in example 4 was 2.4 divided by 12, right? Okay. The present value is what you took out, so that would be negative 16,000, right? Negative 16,000. 0 for payment, we're not doing that. And we want positive 20,000 at the end. So let's go back up. Remember, this N is where the T is kind of hidden. Because we would have put 12 times 5, it's 5 years, right? So let's see what happens here. What do we get? 111.68. And you think, well, that's a lot of years, but it's not years, is it? Right? Because it's compounded monthly.
111 years.
Yeah. Well, that's hardly worthwhile, right? That's a whole life thing. Right, so if you did TVM, if we did the TVM, I'm never gonna die.
Well,
You got 111.68 months. Take that and divide it by 12. What do you get? You should get 9.3 years, right? So you see the trick there. If you want to check yourself with that, you got to be careful. Now, if it was compounded quarterly, you would divide by 12 that end thing. What would you divide by? 4. You get the idea? Okay, so that's a little bit trickier to think about. Okay.